Okay, so we'll pick up with frequency response today and go into some more specifics on how these concepts can be applied. What you learned last time is fundamentally this idea of frequency response is that if you apply a sinusoidal input with frequency omega to some linear and time invariant system, you're always going to get a sine wave of the same frequency in the output. It's always going to be the same frequency. The only difference is that it's going to be scaled by some magnitude, and it may or may not be phase shifted by some amount as well. Okay, and then it turns out again that these two parameters, the magnitude and phase, these are both functions of that input frequency itself. So as you change the frequency of the input sinusoid, the output is going to change in its magnitude as well as in its phase. And then to characterize the system, if you were to plot these two parameters together on the frequency scale, you get something called the Bode plot. Okay, so the pair of plots, magnitude and phase, together plotted against the frequency argument, those produce the Bode plots. Okay, and the Bode plot for a transfer function, for the Bode plot for a system is a visualization of the frequency response, which is a very powerful analysis tool, and as it turns out, a control design tool for later on. One example that we looked at last time was the simple transfer function that has the form of a over s plus a. Okay, so a very simple first order transfer function of this form. Um, it turns out that this is called, in general, this is called a low pass, a first order low pass filter. And today in the lecture, we're going to kind of explain what that means and its application to certain engineering fields. Okay, so let's start by drawing out an electrical circuit. So I promised you guys we were going to do some electrical circuits before the end of the semester, and so the frequency response concept is a very good sort of medium for analyzing these electrical systems because there are filters directly relating to this field of electrical engineering. Okay, so the filter is very simple. The voltage across these two pins is called voltage in or V in. The voltage across these two pins is called V out or voltage out. And it's very simple. There's one resistor and there's a capacitor here with capacitance C. We know that we can model this electrical system. We'll get into the details of that a little bit later, but we can actually model this system and we can come out with the transfer function from the input voltage to the output voltage, right? So this is just any old transfer function like we've derived in the past, only because it's an electrical system, the tools that we use to model it are slightly different. Okay, so we're going to go over this modeling process later in the course, but for now I just want to highlight a couple of interesting things about this particular system. Okay, so if we were to go through the whole modeling process and come up with a transfer function for this electrical system, this is the transfer function that we would get. And it happens to have the same form as that low pass filter, that A over S plus A form that we just talked about here. Okay, so we call this a low pass filter, and any transfer function that has that form has these low pass filtering properties. Okay, what do we mean by low pass filter, however? Well, we know that if we look at the Bode plot for any transfer function of this form, what we get is something that looks like this. Remember that Bode plots are always functions of frequency, and the pair of plots that makes up the Bode plot is the magnitude and the phase. Okay, so if we were to plot out what the Bodie plot looks like for this low pass filter, we get something that looks like this. Okay, so we get something that looks like this, where this frequency right here is referred to as the cutoff frequency, and it's exactly this parameter here, right? So A over S plus A, the cutoff frequency where the magnitude starts to uh, dip down and attenuate, that frequency is called the cutoff frequency for that particular filter. Okay, the reason this is called a low pass filter is because specifically it allows low frequency signals to pass through it largely unattenuated, which means basically the input will equal the output. The input will approximately equal the output. Whereas for higher frequencies, we start to see a lot of attenuation. So it does not allow high frequency signals to pass through. In fact, those signals are all going to be squished down or attenuated, as you can see here in the Bodie magnitude plot. So what we can do is we can actually verify this analytically. So we can use some of the same tools that we've been using all semester to verify this. Okay, so let's take a couple of frequencies. Call this frequency A. This will be a low frequency. And then way over here, we'll consider a much higher frequency. Okay, and again, what we should expect is for the low frequency input, the output should be essentially equal to that because it hasn't been really attenuated at all. The magnitude is still 1, and the phase is roughly 0. It should almost be the same input that we applied. Whereas the output, we should expect to see a lot of attenuation, and we should also see actually that the signal is a bit out of phase. In fact, it should be about 90 degrees out of phase from the input. Okay, so if we were to actually compute this, which we know how to do, let's take frequency A for starters. Frequency A, so let's set up our transfer function. Let's just let R and C both be equal to 1, which simplifies our transfer function a bit. Our 1 over RC over S plus 1 over RC, that just boils down to a simple first order transfer function like this, 1 over S plus 1. And for frequency A, we'll just let the input voltage equal sine of a very small frequency. Okay, so we'll say 0.1 t. So the frequency is 0.1 radians per second. Okay, what this means is, okay, so if you look at our transfer function, that's the relationship between V in and V out, just as always, right? The Laplace of the output divided by the Laplace of the input. If V in is equal to sine of 0.1 t, we know that big V in of S is equal to just the Laplace transform of this, which works out to 1/10 over S squared plus 1/10 squared, or 1 over 100. Okay, so we have the plant, we have the Laplace of the input, which means mathematically we should be able to compute a forced response, which is essentially, right, if you just rearrange this transfer function, multiply both sides by V in of S, you get that V out is equal to 1 over S plus 1 times V in, which is what we just derived over here, S squared plus 1 over 100. And then V out of t just becomes the inverse Laplace of all of this, right? So the actual output, as always, just becomes the inverse Laplace of that stuff on the right-hand side. Okay, so this is going back pretty far, but we know that big V out of S, that can be written, that can be broken down, and we're not going to do all of this, but just as sort of a refresher. This can be broken down using partial fraction expansion as A over S plus 1 plus, and now we've got a quadratic term here, so this will be BS plus C over S squared plus 1 over 100, like so. right? And then what we have to do is, okay, we have to get common denominators, equate numerator coefficients. This is going way back, but it's a good reminder of how to solve these problems. We end up with the numerator, so we need to get a common denominator. So this term here, a over s plus 1, will be multiplied top and bottom by s squared plus 1/100th. And this term here, bs plus c, will be multiplied top and bottom by s plus 1. And that will leave our numerator looking something like this. 1/10 is equal to a times s squared plus 1 over 100 plus bs plus c times the quantity s plus 1. So this becomes our numerator of the above equation here. Trying to be brief here, what we have is we need to expand out this numerator and solve for the coefficients. So on the left-hand side, 0s squared plus 0s, 0s squared plus 0s plus 1/10. Expanding out this numerator, we just get a plus b s squared plus b plus c s plus a over 100 plus c. Okay, and of course this is going to create three equations and three unknowns. So from here we should be able to solve for a, b, and c. And of course we get that a is equal to 10 over 101, b is equal to minus 10 over 101, and c equals 10 over 101. Okay, so you can verify those numbers, but this is just going back to our partial fraction expansion. What this allows us to do is to rewrite the original, this should be v out. This allows us to write our original s domain variable, v out of s, in terms of those updated variables in the partial fraction expansion. So we get 10 over 101 over s plus 1. Now we have a minus. We'll factor out the b term from the bs plus c in the numerator, and we're left with s minus 1 over s squared plus 100. And then this guy should be taken care of. We know how to take the inverse Laplace of this. We just need to work on this guy for a minute, but this is relatively straightforward because this can be broken down into minus 10 over 101 s over s squared plus, and we'll leave this as 1/10 squared, plus 10 over 101, and then the other one would be 1/10 over s squared plus 1/10 squared, but because we factored out that 1/10, we need to multiply by 10 on the outside. So all of this is going to translate to, we need to take the inverse Laplace of this, and this, which is easy to do now because all of those terms are in a form that appears on the Laplace table. Okay, so we can actually now go to compute v out of t, and we're going to get from this guy 10 over 101 e to the minus t. We're going to have a minus 10 over 101 cosine of 0.1 t plus 10 times 10, that's 100 over 101. And this one's going to give me sine of 0.1 t. Okay, so this is our actual output. This is the actual voltage output if we were to apply this input, sine of 0.1 t, into the low-pass filter that has this Bode plot here. Okay, so we're looking at, again, frequency A here. A low frequency should allow, the filter should allow that low frequency to pass through if it's a low-pass filter. So how do we make sense of this? Well, the first thing to note is that the frequency response plots, in other words, the Bode plots, those tell us about steady state output. Okay, so the Bode plot only tells us about the steady state output, which is, as we know, once all the transients have decayed, what is left over. That's what the Bode plot tells us. Okay, so in this portion of the output, we see a transient portion, and we know that that's going to go to 0. Okay, so this part isn't even considered on the Bode plot. That's all going to decay. And then what we have left over is essentially, if we write it out in decimals here, we have minus, well, we have roughly 0, right? Because we have this factor of 10 over 101, which is less than 0.1 times a cosine factor. And then over here, we have 100 over 101, which is basically 1, times the sine of 0.1t. Now, the input itself was 1 times sine of 0.1t. So what we're seeing here is just basically the same as the input signal. Okay, so you have something that's, small, relatively speaking, plus something that's basically equal to the input as our entire output. And so what that looks like ultimately is V out is equal to, right, you have minus 0.099 cosine of 0.1t plus 0.99 sine of 0.1t. Okay, so what this looks like on the time scale is basically 99% of the output comes from this, and maybe 1% of the output comes from this cosine. Okay, so what you end up with is basically a sine wave of frequency 0.1 t, like this. This is your V out. Now you have to remember that V in of t was exactly equal to 1 times sine of 0.1 t. Right? So the input looks basically like this. It's almost the same, right? Maybe it's just slightly out of phase due to this additional cosine function in the output here, which constitutes about 1% of the total output. But largely what you're seeing here is that the output is equal to the input. Okay, and so what this means is back to our, right, so this is for the low frequency A. What we're seeing is that basically at this low frequency, the low frequency sine wave is allowed to pass through that frequency unaffected, right? So the output is essentially equal to the input, which is what we're seeing here, right? This is one of the key traits of a low pass filter, is that it allows those low frequency components to pass through unaffected. If we do a similar thing and look at a higher frequency, remember at high frequencies, the Bode plot says that we should be highly attenuated. That means the output is basically squished close to 0. We should see that at very high frequencies, that signal is really not allowed to pass through, which just means that it's going to be very much attenuated. Okay, so for this case, we could consider a frequency, right, not sine of 0.1t, but maybe sine of 100t. So this is a much higher frequency signal that we were trying to pass through this filter. Well, a lot of the analysis stays the same, except that the nature of the Laplace of the input changes. Okay, so big V of s, if little v of t is sine of 100t, becomes 100 over s squared plus 100 squared. Okay, that's really the only change that we see here. The rest of it is to compute V out, and we won't do this whole thing, but the computation, the setup for the computation is exactly the same. V in of s, right? Which looks like 1 over s plus 1 times this new V in of S, which is 100 over S squared plus 100 squared. Okay, so we'd have to do again a similar partial fraction decomposition, solve for the coefficients, but at the end of the day, what you end up with is, right? So we'll do a little bit of skipping here because the math is very much the same. Big V out can be expressed as 100 over 10,001 times 1 over S plus 1 minus this same parameter times S over S squared plus 100 squared plus 1 over 10,001 times 100 over S squared plus 100 squared. Okay, so all I did basically was the same exact math as the previous problem. It's just that the coefficients have changed in their value. Okay, remember that when we take the inverse Laplace of this, that's going to be the total output voltage. Okay, so the inverse Laplace of this becomes V out of t, 100 over 10,001 e to the minus t. Again, this is just transient behavior, so that's going to just all decay to 0. Then you've got minus 100 over 10,001 cosine of 100t plus 1 over 10,001 sine of 100t. Okay, so what this looks like in steady state, not S, what this looks like in steady state is the transient is decayed, and we have essentially minus 0.0099 cosine of 100t plus 0.00099 sine of 100t. Okay, this is our actual output of the filter if you try to pass a sine wave of a frequency 100 through it. Right? So all we did was compute it mathematically here. But what you can see is, okay, this is on the order of 0, and this is more so on the order of 0. That 0.00009 coefficient out in front really demonstrates a lot of attenuation. Okay, so it's not as though the filter magically zeroes out the output. It's just that the magnitude is so attenuated that it's almost as if the signal is totally squashed out. Okay, if we look at this on the time scale, remember that V in is sine of 100t. So the input has a much higher frequency. Right, so the input frequency, maybe this is sine of 100t. Right, so it's a high frequency of magnitude 1. The output is still a sine wave, just like all systems. Right, if you apply an input of a sinusoidal nature, like I said, you're going to get an output that's a sinusoid. It's just that the magnitude and phase values depend on that initial frequency or that input frequency. So our output voltage here, which we just computed, it still has a sinusoidal form. It's just that the amplitude is really, really small. So if this is 1 here and negative 1, well, we've got a sine wave that's got a magnitude of 0.000009, so maybe that's like here and here. And then this sine plus this cosine produces an overall effective sine wave that's out of phase from the input. So our output may look like this, right? What I'm trying to draw is that it's still a sine wave, but the amplitude is so small that it's practically just a zero signal. Okay, and this goes to validate the concept of the low pass filter, which is, again, the filter allows low frequency sinusoids to pass through, but it severely attenuates higher frequencies. And higher is a relative term. That just has to do with where the cutoff frequency is for that particular filter. Okay, so by choosing R and C properly, okay, you can actually decide where this cutoff frequency resides along the frequency spectrum. Right? So you can choose to filter out really high signals and allow lots of low frequencies to pass through, or you can set it really low so that you only let really, really low frequencies through and sort of squash everything else above that frequency. Okay, so this is an illustration or sort of a demonstration that's supposed to reinforce the concept of the frequency response, but also give you sort of an application of how this works in a filtering sort of standpoint. There's many different types of filters that are available. In the future, we'll talk about not just low pass filters, but high pass filters and even band pass filters. And the so-called notch filter. So there's many different types of filters that we can build, and they all have different properties when it comes to the frequency spectrum. So what we can actually do is verify some of the things that we just computed analytically, numerically. So we can allow MATLAB to do a little bit of filtering for us so we can see what the output looks like. And hopefully it'll agree with the analytical computations that we just performed. Okay, so in MATLAB we can always define our Laplace variable, which allows us to write transfer functions in terms of that variable s. Okay, so the transfer function we were dealing with was pretty simple. It was just 1 over s plus 1. What we can do is to define a time vector, because what we're going to do is basically simulate sine waves of different frequencies and pass it through this filter of 1 over s plus 1. So just as always, you can define a vector in MATLAB using this notation, which is basically just saying go from 0 to 10 seconds in increments of 0.01. So we're building a little time vector here that will go for 10 seconds. And then using this time filter, we're going to build our input signal. So we want the input voltage to be a sine wave, to have, we'll start with a low frequency of 0.1 t, right? So this is going to be our input sine wave. And if you're curious as to what that looks like at this point, we can just plot t against v in, and we can just see what that looks like. Oh, we're going to need more time here. Let's see. Let's allow this to go to 100 seconds. Okay, so we can see what our input sine wave looks like at a very low frequency. Okay. What we want to do is actually pass this low frequency sine wave through this filter and look at what the output gives us. Okay, so one function in MATLAB is called the LSIM function, which is really useful. We could define Vout is equal to LSIM, which I think stands for linear simulation, and then you have to give it the transfer function you want to apply the input to. You need to give it the input, and you also need to give it how long you want it to run for. Okay, so what this line of code is doing is it's passing this input, Vin, through this system for this amount of time. Okay, that's all this line of code is doing. And then that's going to give us one output, V out. But what we want to do is visualize this output superimposed on top of the input to see, hopefully, that for very low frequencies we see an output that's roughly equal to that input. So we can go ahead and plot our input. And we'll make that blue dashed line, and we can plot that against the output, which is V out, and we'll make that a solid red line. And then we'll want to define the input. So we're going to have, so the first argument was the input voltage, so that'll be V in, and the second one is going to be V out. Okay, anything else we need? We'll throw a grid on there just to see, and if we run this, we should get a nice plot that shows us the input voltage, which is the dashed blue line, and then the output voltage, which is the solid red line. Okay, remember that this is for sine of 0.1 t. So what we are expecting to see from the Bode plot is that we get basically no attenuation. We have an amplitude that's basically 1, and a phase that looks like it's slightly out of phase, right? So one other thing we could do is we could even plot, we could look at the Bode plot of P itself to verify what we should expect for that particular frequency. So if I put a grid on here, change the magnitude to absolute, we can actually zoom in to, so a frequency of 0.1, that's 10 to the minus 1, that's right here. We can actually see that our magnitude is basically 1, right? Or 0.995 at that frequency. And our phase is negative 5.6 degrees at that frequency. So just like we saw in the plot here, the magnitude is 1, but we do see that it's slightly lagging behind the input, right? So the red is coming slightly after the blue plot, which agrees with that minus 5.5 degrees of phase lag or so. Okay, so that's exactly what we're seeing here. If we were smart, we would go ahead and put these on the same axis so that we can see. So what we can do is just do a subplot here, subplot 1, 2, 2, and we can look at the Bode plot for P on the same sort of figure. That way over here what we have is basically you can verify for that particular frequency, and we just see it all in one place. Okay, so let's turn our grid on here. So just like before, at that frequency, now we've got it all in one place. We see the magnitude of practically 1 in a phase of about minus 5.5 degrees. That's exactly what we're seeing here in the time domain as we plot the input voltage and the output voltage. It's easy enough to see what happens at higher frequencies. All we have to do is change the frequency of the input. So remember that by hand we computed two frequencies, 0.1 radians per second as well as 100 radians per second. What we saw for when we plugged in a much higher frequency is that the amplitude or the output was highly attenuated. So the output was squashed nearly to zero because of the nature of the low pass filter. Okay, because this is such a high frequency, we're gonna limit the amount of time that it has to run, because otherwise we're just gonna see blocks of red and blue. So if we were to plot this, yeah, we still kind of see that, but that's okay. I'll go ahead and do a little zooming for you. On the remember, we're now at a frequency of 100, so we're way out here. At a frequency of 100, so we're expecting our magnitude to be really small, approximately, if it'll let me, approximately 0.01 relative to the input. Okay, and so that's what we're seeing over here. If I zoom in on these sine waves, right, if I zoom in a little bit more to make it a little more easy to visualize, you can see that again the input is still that sinusoid with an amplitude of 1, only now the frequency is much higher. And as we can see, if we try to pass that signal through this low pass filter, we're over here on the Bode plot. And so at that frequency, the magnitude is going to be really, really small, which we see on this red plot here. Okay, so the red plot is actually a sinusoidal function. It's sort of oscillating up and down. And furthermore, it's out of phase by a lot more than just negative 5 degrees, right? So we're at negative 90 degrees lagging behind the input, which basically means every time we hit a peak on the input, we should be passing through 0 on the output, and vice versa, which is precisely what we're seeing here. So if I were to zoom in even more on just the output side, of course the scale is going to change, and we can see that we have that amplitude of about 0.01, which is really highly attenuated compared to the input. Okay, so that's what we see over here. Okay, so this is a really good way to use tools like MATLAB to visualize um, what's going on with the frequency response. Okay, so if I change the time to just 1 second, it's a little bit easier to see. But we could actually change the frequency here to anything that we want, um, and just verify that anywhere along the frequency axis of the Bode plot, we should see a corresponding magnitude and phase in the output. Okay, so this is, you can keep this code, you can mess around with it. All you're really changing is the frequency here. Maybe we'll do one more. Right, so we did 0.1. I've got to change the amount of time it runs for. We did 0.1 before, and what we saw is that the magnitude is basically 1 in the output, but we saw that little bit of phase shift, and that was, of course, because at 0.1, there's this little bit of negative phase. Theoretically, if we make the frequency even smaller, we will be going back towards the left on the frequency spectrum, and we should actually approach phase of 0 degrees. So maybe we can try for a really, really small frequency, like 0.001. We can see what that looks like. Well, we'll need to run this a little longer, looks like. Oh yeah, we're going to run it a lot longer just to get through one cycle. Right. Okay, well, let's do even longer. Hope this doesn't break MATLAB. Ooh, we might have broken MATLAB. Okay, no. So we're still good. The reason is I'm running it for a really long time because this is such a low frequency. It needs a lot of time to complete one cycle. But because I extended the time and I'm sampling at 0.001 seconds, we've got data sequences that are now over 1 million or 10 million elements long, which is taxing on a computer. But it's fine. Our computer should be able to handle it. Okay, so now if we look at the input-output, we are now way, way back here on the frequency spectrum. We're at like a frequency of 0.001. So in fact, I need to change the axes on the Bode plot to even see that. But I can do that. So I'll make it go to 0.00, maybe, yeah, one more, why not? 0.0001. And so the frequency that we just passed through was 0.0, let's see, 0.001 radians per second. So that's actually 10 to the minus 3 back here. So we're expecting to see an amplitude of basically exactly 1 and a phase shift of 0.09 degrees. So almost no phase lag at all. And again, that's exactly what we're seeing, right? We really have to zoom in here on the input-output plot to see any kind of discernible phase lag at all, right? We're basically right on the money. There's right there, if we zoom in this far, there's your 0.0956 degrees of phase lag right there, okay? So there's a lot you can do with this code if you want to mess around with it, but the whole point is to give you a little demonstration here about really the effect of the frequency response and its application to filtering. Okay, so I'll leave it at that for now. This is supposed to be a little bit of reinforcement of the frequency response concepts and sort of one application of where it's used in industry a lot, which is this concept of filtering. What we're going to do in the coming lectures is to develop a method for sketching the Bode plot or the frequency response for really any arbitrary transfer function that I could give you. And then we'll look at more electromechanical systems as our sort of base type of system. So we'll look at different filters, low pass, high pass, band pass filters, and then we'll even get into some electromechanical systems like DC motors, all under this umbrella of studying the frequency response of the particular system. Okay, so we'll see you in the next one.